Next, we will discuss time synchronization. Time synchronization involves the Network Time Protocol, or NTP. This protocol is used to synchronize time between devices. Its main purpose is to enhance the readability of logs. It's not the main thing, but it does improve the readability of logs. At the same time, it means that for our devices, when we configure our devices, it will display a message like this. This message, we call it a log. That is, a log with a timestamp in front. So, if we say our network inside, if the time on these devices is not the same, at that time, for instance, in our network, suddenly there is a jitter, or we say in our network, suddenly at a certain time there is a fault, then by looking at the log, if we want to trace back, it becomes very difficult at that time. So, in our network, we usually need a time source, and other devices, they find this time source to synchronize time. In this way, all the network devices in our network will have their clocks synchronized. In this way, the log information, we can look at it horizontally. We can look horizontally at other devices to find log information. And then, by looking at multiple devices, viewing the same log information at the same time, we can trace back to what happened at that time. Here, our network devices, they also need to synchronize time. Here, of course, synchronization of time is through the NTP protocol. The NTP protocol, it works like this. NTP protocol, it has levels from 1 to 15. 1 to 15, and level 16 means unsynchronized, which is 16. From 1 to 15, the smaller the number, the more precise. The smaller, the more precise. Why? Because with NTP, you need to synchronize time, right? It's like you are a client looking for a server to synchronize time. You have a host that needs to synchronize time. It finds a server to synchronize time. And as time goes by, we, at a certain time point, like we are at point A. At time point A, the host goes to find the server to synchronize time, right? At this time, he goes to find the server to synchronize time. But at this time, at point A, he sends out the NTP packet. Then, the server on side B receives it, right? At point B, it's received, and then B then sends back the reply packet. The server replies to the client, and at this time, that's how it works. For instance, we're at time point A. At time point A, the host seeks the server to synchronize time, right? At that moment, he goes to the server to synchronize time, but at that time, at point A, he sends out the NTP packet. Then, the server on side B receives it, right? At point B, it's received, and then B then sends back the reply packet. The server replies to the client, and at this time, that's how it works. The server replies to the client, and at this moment, on side A, at node C, the packet is received. At that time, right at that moment, they engage in two-way communication. This is known as the round trip, right? Two-way communication. So then at that time, there is something which is the RTT. RTT refers to round trip. That is the round trip time. At that time, from A to C, the duration from A to C is the round trip time, right? But at that time, B replies, where in the NTP packet is the timestamp? It's at node B. So at that time, at that moment, the NTP reply packet will carry the NTP server's server reply timestamp. At that moment, how does the client know? He divides the RTT by 2. By dividing the RTT by 2, he estimates a point called B. At that place, we might call it B, based on the round trip time divided by 2. Then he can calculate a time point called B. That's half of the RTT, because at node AB, from the A time node, you send out the NTP request, and then the server on side AB receives and replies, and A receives it at node AC. At that time, the client divides the round trip time by 2. To get something like B being this point, he assumes it's approximately similar to time EB. So each synchronization actually has a slight deviation, right? So the smaller this number, the more precise the time. The larger the number, the less precise the time. If you synchronize with a level 1 server, you become level 2, you are level 2. If the server is level 2, your synchronization would make you level 3. You add 1 level each time you synchronize. If it's 16, that's unsynchronized. Generally, it's between 1 to 15. We don't use too small a number if we haven't deployed a dedicated time source. If we haven't, I recommend not using too small a number. Here, usually we default. If we say within our own network, we use a router as the time domain. As the NTP server, it's usually level 8. Why can't you use below level 8? I'll tell you, you can't use level 1. Level 1 refers to the cesium atomic clocks at Greenwich Observatory. That's level 1. Satellites are level 2. Then just think, if you say, right, can you use level 1? It's not that you're not allowed to use it. I'm telling you what level 1 is. You probably won't use level 1. NTP clock level 1 means the cesium atomic clocks at Greenwich. That kind is level 1. Satellites are level 2. Then just think, if you say, can you use level 1? It's not that they don't let you use it. I'm telling you what level 1 is. You probably won't go for level 1. NTP time hierarchy level 1 refers to the cesium atomic clocks at the Greenwich Observatory. That kind is level 1. Satellites are level 2. Then just think about it. If you establish your own network and say you've set up an NTP server, then you set this clock to level 1. Here, if you point to multiple NTP servers, the one with the lowest stratum level has the priority. That's usually how it works. So, if you set your own clock level very low, it's possible that you might not be able to sync the real time anymore. So, typically, the NTP protocol requires a time source. At that point, all devices must seek this time source to request time. But if the NTP messages are tampered with by an attacker, it could disrupt device operations by altering the system time. In such cases, what do you do? If someone attacks your network, inside our network, we rely on system knowledge to log some information. But if an attacker targets your time source first, making your time inaccurate, it could lead you to find your logs showing strange timestamps, like why is it saying it's 20,990? In such cases, your logs, when were they actually made? You wouldn't know yourself. So here, how do we prevent NTP messages from being tampered with? Here we can set up NTP synchronization with authentication, meaning the NTP authentication effectively requires your client to authenticate and the server to prove its legitimacy. This way, it means your serve. This means that your server must prove it is a legitimate server, not one that's a counterfeit by others. In other words, your time synchronization must be reliable when syncing with me. Only then it won't affect my system. So, here we can configure this N authentication for clock synchronization. We can set up authentication in NTP by configuring to initiate it. Here, the server is required to provide its proof of legitimacy. That is to prove, what does this mean? It means when you, the client, seek to synchronize time with the server at the time of synchronization, you, the server, are required to provide credentials to prove your authenticity. Simply put here, both parties need to configure a key. Through what? What is this? It involves a key, namely a key-based hash, which is HAC, right? It uses HAMC for authentication. So, with this, we can ensure the security of NTP through this authentication. Next, regarding system logs, having just discussed time, now about the system logs. The system logs record information from devices based on certain information. These typically include system information or system events or network events. These are the logs recorded down. Here, they can be logged to the console, which we're seeing now popping up as the console. Of course, if you access via VQI, in that case, the console is what pops up. That's the case. We can log it to a monitor. When logged to a monitor, meaning you remotely log in via a VQI thread, managed through command line, you can see the logs. Of course, there's a toggle command that we must enter to access. Besides logging to the console, logging to VQI, it can also log to where to the buffer. Buffer means cache, which means for us, our network devices like routers and switches, they are essentially, let's say routers are essentially computers. They have their own CPU. They also have their own memory. So here, their cache is a segment slid out of memory, a space where we can store commands. We can store these logs. We show logging. We can see where these logs are recorded into this buffer. But this memory is RAM, gone upon restart. So what do? You say, what if my device crashes? I want to know why it crashed, whether the CPU was maxed out or the memory burst. What exactly was the reason? Right, why did my device crash? So here we want to see the log, right? But what do? The buffer will definitely not show it post restart. So what we can do is specifically log it on a syslog server. We specifically use a dedicated host to gather all logs from every device in our network and store them on a specialized server. This server is responsible for their long-term storage. This is what we call a syslog server. But to deploy this syslog server, the same premise applies. What is it? Time synchronization, right? Otherwise, in your network, if you defeat a device, its time will be all over the place. Looking at the same device, you wouldn't know what is related among logs from different devices. So, if you're logging, and if you do it this way, you absolutely need to maintain time synchronization. Of course, we can use the SNMP protocol to actively push logs to an SNMP server. These system logs are typically used for monitoring and auditing. In case of anomalies in the network, these types of logs are usually utilized. When an abnormality occurs, we can trace back what event happened. Then, during system operation, if there are some critical nodes, like for instance what configurations we made, or which interfaces went up and down, etc., these are the kinds of events that would generate system logs. Here, by default, they output to the console. If you don't connect a console cable, or if you do but don't open their interface, you won't see it. You won't be able to see it. That's the situation. If you log to this buffer, the memory cache has limited storage capacity. It can be overwritten, right? You understand this, right? And it's gone upon a restart. So this means it's not reliable. So the best way is to save it on a dedicated log server, what we call a syslog server. Once saved there, in this way, multiple devices can send their logs to the same server for storage. This way, we avoid losing or deleting them. So here's the requirement. Time must be synchronized. Otherwise, it doesn't make much sense. Logs are graded by severity from 0 to 7, with lower numbers indicating higher severity. Here, for us, a lower number means a more severe event. So here, our place, the logs are like this. They are tiered, with level 0 being the system is down, right? Level 1 is critical. Then level 2 is alert. Level 3 is errors. Level 4 is warning. Level 5 is notification. Level 6 is informational. Level 7 is debugging. Here, the lower the number, the more serious it is. So here, basically level 0 you basically won't see. Because level 0 means essentially, it means the system has crashed. Gone. The system has hung up. Can it be seen? It's really just luck. What does that mean? Can you see level 0? Level 0 logs are like, say, a person falls from the 5th floor compared to falling from the 50th floor. What's the difference? Right. Falling from the 5th floor might leave you bouncing, right? But from the 50th floor, it's a bigger impact. Can that be heard? Right? You see, there's no time to shout out. So here, this level 0 log is basically hard to see, right? It's likely just a crash, not just a crash. So in this case, of course, other logs, the lower the number, the more critical they are. Because the lower the number, the more severe the situation. Here, at this point, of course, you can manually tag logs that you are concerned about. You give them a chip, you chip them, or even you can use something like scripts for matching. In these cases, some details we'll cover in the NP and IE phases. We'll discuss system logs. Okay, good. Then, regarding CPU and memory alarms, CPU and memory alarms are like this, because it's possible that our system might be under some attacks. If our control layer is attacked, what might happen? If the control layer suffers an attack, it could cause, for instance, memory exhaustion or memory overflow, right? Or the CPU being maxed out. In such cases, in these situations, our system might experience some issues. Possibly, right, the system might crash. So in this case, do we have a way, right? Can we, right, before it reaches a critical point, be proactive and send out alerts so that it means we have a few methods. One way is through network management software to then read and periodically retrieve performance metrics. This is called monitoring, right? We have to deploy some monitoring platforms in our network. This method, this approach, speaking of which, if you have the budget, that's great, right? But if the budget isn't that tight, you say, on this device, set up something, set a threshold. After setting the threshold, when exceeded, it generates logs and alerts. Of course, you can also push it to somewhere, push it to such network management software. Of course, you could also send it to a size log server. There we can configure the memory reservation, how much memory to reserve. Then if the memory falls below a certain level, trigger an alarm. Then if the CPU reaches that threshold, trigger an alarm. CPU triggers an alarm, reaches that set point, trigger an alarm. This is possible. Of course, you say, if you want to go advanced, you can trigger an action through these alarms, trigger something called EEM, which is this thing, this EEM thing is like a trigger. It's essentially a trigger. You can use certain events, like say an alarm, for example, right? This alarm, like a specific log or an interface goes down, right? For example, right? I'll set alarms here, then it can perform a series of operations. Like we're sort of doing something similar. It's like we're doing something similar. It's like setting a trigger that activates under certain conditions. It will trigger the execution of certain commands. With this method, we can use some approaches to solve this problem. After all, we are not on a 24-hour watch, so we definitely need to implement some safeguards. And another thing is NetFlow, the Network Traffic Analysis Protocol. NetFlow is designed to capture and analyze traffic data from our network devices. We deploy a server within the network, a server that is equipped to handle NetFlow data. This protocol helps in analyzing network traffic patterns. Essentially, it collects and summarizes the traffic data, allowing for detailed insights into network operations. For example, on the network devices, we can configure NetFlow to capture incoming and outgoing traffic summaries. These summaries are sent to the server, which analyzes the data. This setup helps in maintaining network efficiency and identifying potential issues before they become critical. This way, we ensure that our network remains robust and secure. By deploying NetFlow, we can keep a close watch on the network's health and performance. This proactive approach helps in managing network resources efficiently. Not just summary values, but detailed traffic information is analyzed. Send it. Explain this method. What is meant by summary information? In this case, you can understand it as if traffic were a book. Its summary information would be the table of contents. That is, it takes some of the summary information and sends it to the server for the server to analyze. In such cases, the server, generally speaking, is also a monitoring platform. In this regard, or some network behavior analysis, it here collects information from the packet headers according to the flow that is according to this flow to classify. Here in such a way, then it can tally the traffic and analyze traffic composition proportions and many other things. Then there are these network management platforms. They can receive through SNMP protocol periodically. They can also receive through NetFlow protocol. In this way, it can provide you with various reports you created, like what topology maps, bar charts and such, then presenting them very clearly. The so-called 7-tuple here below source and destination IP source and destination ports, protocol number TOS, root interface. Through this 7-tuple, it goes to classify the traffic, that is, it assumes, right, generally, these types of flows like the 7-tuple are often from the same plan. Through these parameters, it classifies the traffic. In this way, it's available for societal analysis. That's NetFlow. We can use it to carry out to obtain some information inside the network. This then comes the Configuration Management Protocol. Configuration Management Protocol, we've already configured it. Disable Telnet switch to SSA. In our transport input, you can specify a single protocol or multiple protocols. You can also specify none, meaning nothing is allowed. In this case, we communicate. That is, if we use a CLI for management, we use line VTY. Of course, we can also manage through HTTP. The difference between HTTP and HTTPS is HTTPS is encrypted, HTTP is in plain text. So we should choose a management protocol that can encrypt data whenever possible, such as SSH using Secure Shell and HTTPS using SSL, the Secure Socket Layer. We should choose an encrypted protocol whenever possible, like SNMP, Simple Network Management Protocol. And we can choose version 3. Why choose version 3? Because it is encrypted. Version 3 can encrypt data. What this means is that we should use protocols that encrypt traffic. Don't let management traffic run unencrypted on the network. If your management traffic is unencrypted in the network, it won't be long before your entire network is exposed. This is about configuring its management protocol. Next, SNMP. Here, let's do this. For today, we'll stop here because of time constraints. We'll talk about the rest in the next class.